All right. So the last problem I kind of rushed at the end, but I think you can do it. You can plug in the numbers. So let me go to uh, the last problem in this chapter that I wanted to do, chapter 7. I would go to chapter 8. As you see, very similar problems, except you would have motion on a plane, mostly circular motion. So you have a 2,000 kilogram cable car descends a 2,000 meter high hill. So this is the car, and this is the hill. It's initially at a height of 2,000 meters. I believe it's 200 meters. Let me just double check that. Yeah, it's a 2,000 kilogram car descends a 200 meters. So yeah, this is 200 meters. 200 meter high hill, so it's here and it just descends. And so it's connected by a cable to this mass here. It's called a counterweight, just to make sure that the car slowly goes down. And they say assume the rolling friction. It has wheels, and so let's assume the rolling friction is negligible. It's just negligible, nothing. The counterweight is 1,800 kilograms. And then it says the cart, to control its speed, it's connected to the counterweight. That's great. And then the cart also has brakes. So it has brakes, so it's braking, so the brakes will also apply an additional force backward. Okay? Will apply an additional force in the backward. So there is tension this way, and then there is the braking force this way. And then there is a component of mg downward. Okay? All right, let's continue reading the problem. It says, how much braking force does the cable car need to descend at a constant speed? Constant speed. Along a straight line, it means the acceleration is 0. So, this is motion with 0 acceleration. So let's do part A, and then we'll go back and do part B. Let's do part A, because I have to erase, I don't think I have enough space to do parts A and B in one space. So I'm going to take my positive, negative directions for, let's look at the 2,000 kilogram car first, and then we'll look at the 1,800 kilogram counterweight, and then consider them together. So here is the car, looks like this, and I'm going to call this one here M1, and M1 is 2,000 kilograms. And this angle here, I'm going to call it theta 1 because I have two angles, theta 1. And theta 1 is 30 degrees, right? 30 degrees. So what are the forces here? Oh, gravity, straight down. M1G. What else? There is the normal force. N1. Yeah, all right. And then there is the tension from the cable. And then there is the braking force, I'll call it F. Anything else? Well, that's it. It's connected by a cable. It's touching the hill, so there is a normal force. It's on Earth, there is gravity. They say there is no friction. Don't worry about rolling friction. That's it. Now, I'm going to say M1G will have two components. One of them is this way, M1G cosine theta. That's equal to the normal force because there is no motion perpendicular to the plane. And then there is the M1G sine theta. And I'm going to choose my x and y coordinates accordingly. I think it makes most sense probably to choose maybe this to be the positive x direction and this to be the y direction. Or maybe up the hill is the positive x direction. It doesn't matter. So we only care about the x direction here because the y direction, there is no motion there. It just gives us the normal force, which we don't care about. We only care about the normal force really, or most of the time we care about the normal force is if there is friction, because it's related to the force of friction. Here there isn't, so don't really care about it. So we say that the net force, this is part A, the net force in the x direction on mass 1 will equal to mass 1 times the acceleration of mass 1 in the x direction. But it's equal to 0. They say it's not accelerating. It's moving at constant speed in a straight line. That's constant velocity. So, what are the forces in the x direction? You get, I said m1g, and I'm choosing this to be the positive x direction, so m1g sine theta. I have, maybe it was a mistake to choose. That's fine. m1g sine theta. In fact, sine theta 1, because I'm calling this theta 1. That's positive because that's the positive direction, down the incline, minus the tension because it's up the incline and I'm considering that to be the negative direction. It doesn't matter. And then minus the force of the braking force, F. And by the way, I know the braking force exists because they told me that it is there. And brakes, it opposes the motion, so it's in the opposite direction. Equal to 0. And so I conclude that, all right, so I have this equation here. So I have this equation here, right? This equation. And let me now look at this mass, that one, that looks like this. Here is theta 2. And here is m2. Question, what are the forces on m2? There is, it's in contact with the hill. So there is normal force, m2. It's on Earth, so there is m2g. Is there friction? No. Are there brakes? No. It's connected by a rope or a string, a cable. So there is tension. Cables only pull, so there is tension that way. And it's the same tension because it's an ideal cable and so on. All right, those are all the forces. And I'm going to break down the m2g into two components. One of them is this way, m2g cosine of theta 2. And there is one component this way, m2g sine of theta 2. Yeah, and then we will say, keep writing in blue, the net force in the x direction on m2 will equal to m2 times the acceleration in x direction of m2. But that's 0. They're connected. If this doesn't accelerate, that one doesn't accelerate. They have to have the same speed and acceleration at all times. Great. So let's write down the equation. The equation will say, what are the forces? Oh, I have to choose my coordinates. It's totally up to us again. I can choose this to be the positive x for this one, and this to be the positive y. As long as it chooses x along the incline in some sense, either down or up the incline, and y to be perpendicular, that's a good direction. Okay, so the positive x direction is down the incline, so m2g sine theta 2, that's positive. So I have m2g sine theta 2, that's positive. And then the tension is up the incline, but that's the opposite of the positive x direction, so that's minus t equal to 0. There is no acceleration. So get that. So this is my second equation. And I have two equations. Well, guess what? I'm going to add them. Because I want the, remember, I would like the force, the frictional force. How much braking force? Yeah, I don't care about, they didn't ask about the tension, so I'm not going to calculate it. All right, so I'm going to add these two equations. Actually, not add them, probably subtract them. Yeah, I probably have to subtract them. Let me multiply this equation by -1 because this is negative, this is negative. I would like this one to be positive. Let me multiply both sides of this equation by -1 just to make it easier. So I'll have the tension minus m2g sine theta 2 equal to 0. And now I will add this equation to this equation. Yeah, this one has a negative tension, that one has positive. So let's add them. So when you add them, the tension goes away, and I will just have m1g sine theta 1. I have m1, let's write in different color now. I would have m1, I'm adding this equation to this equation. m1 g sine theta 1 minus t plus t equal to 0, so that goes away. And then minus f, done with this one. The t cancelled with the negative t there. And then I'm adding, so my plus negative m2 g sine theta 2. On the right hand side, 0 plus 0 is 0. What am I talking about? This is f, not t. F, yeah. Move the f to the other side, so you get f will equal to m1g sine theta 1 minus m2g sine theta 2. Factor the g out. So you would have m1 sine theta 1 minus m2 sine theta 2 times gravity. That would be the braking force needed to go at, that's how hard you have to brake in order to go at constant speed. So again, F would be, we'll plug in. Plug in the numbers. M1 is 2000 and theta 1 is 30 degrees. So I have 2000 times the sine of 30 degrees, which is a half, so I get 1000. And then minus M2, that's what, 1800, times the sine of theta 2, which is 20 degrees. Okay, and then multiplied by G, which is 9.8. So I get 3,767 newtons. 3,767 newtons. I just said the number and I forget what the calculator said. 3,767 looks good. Let me just check the solution to make sure they have the same thing. Yeah, they have 3,700 and they rounded 3,770 newtons. Good. So we have the correct answer. We're done with that one. Make sure my camera is recording. So now, what's the next part? The next part says, one day, the brakes, just as the car leaves the top, so the car is here, the brakes fail. They fail. So what does it mean? It means if the brakes fail, this force is missing, and so the right-hand side will no longer be 0. The car will be accelerating. So the car will just start slowly from 0 to all the way downhill. It will accelerate. And the question is, what would the acceleration be? And then by the time it gets to downhill, how fast will it be moving? How fast will it be moving? Well, let's do part B. I will leave those diagrams in there, and I will show you how it changes. So I'm going to erase here. So what would be missing from this picture? Well, this is part B now. What would be missing is the braking. So F will no longer be there. Okay? F is no longer there. That's what's missing. And that changes the whole story. So we will say, here's part B. Again, we'll say the net force on object 1 in the x direction will equal to. Now, earlier they guaranteed us you have enough braking force to make it move at constant velocity. But now there is no braking force, so it might accelerate. So you have no right to assume the acceleration is 0. They didn't tell us that. Earlier they said, but now you have no right to assume that. So it will equal to mass 1 times the acceleration down the incline. Let's see. I'm assuming this is the positive direction, and the acceleration, let's assume it's also down the incline, so that's positive. So M1A, so that's a positive thing. So what are the forces involved along the x direction? Earlier we had 3 forces because the braking force was also up the incline, but now you just have the tension and the M1G sine theta 1. So I have down the incline is positive, so I have M1G sine theta 1. That's positive. The tension is up the incline, so that's negative, and then equal to M1 times the acceleration, and that's a positive thing because it's accelerating down the incline. That's what I'm assuming. Yeah. I don't think it will go that way because this is heavier and this side is steeper. So again, but then what's the worst case scenario? Let's say my assumption is wrong and they actually go that way. Well, I will get a negative value for the acceleration, and that will tell me, oh yeah, your acceleration is actually incorrect. It should be up the incline instead of down. I'm confident it will be down the incline because that's what they're saying. It will go downhill. So the numbers will work out to be that way. So here's my first equation. We leave it like that. And now let's go to this mass here. What changes in this diagram? Well, everything remains the same. It remains the same. But now we'll have an acceleration. So we will have, along the x direction, we'll have m2g sine theta. That's positive because it's along the x direction. And then the tension will be negative. Yeah, so we'll have the net force along the x direction on object 2 will equal to the mass of object 2 times the acceleration of object 2. They will have the same acceleration because they're connected. But let's figure out, is the acceleration positive or negative? If this one accelerates down, this one has to rise to accelerate up. I'm considering for this one here, down to be positive. So if it accelerates up, that will be a negative. So I have to put a minus sign. Let me put it in red to remind you. Okay? Okay. What are the forces? Well, you got m2g, that's positive because it's down by just by choice of axes. m2g sine theta 2. The tension again is up, so that's negative minus the tension equal to negative m2 times the acceleration. And let me multiply. I see negative tension, negative tension. Let me multiply everything by negative 1 here, so we'll have positive tension. So let me multiply everything by negative. I will have m2g sine, sine theta 2 plus the tension equal to multiply by negative 1 also here. So you get m2 times the acceleration. So now I have this, and these two equations are basically begging you to add them, because when you add them, the tension goes away. So let's do that. Take these two equations and add them. So when you add them, this plus negative this, you get m1g sine theta minus m2g sine theta 2. You will get, let's do it in 2 steps. m1g sine theta 1 minus m2g sine theta 2. And then the tension, negative t plus t, that's a 0. And then m1a plus m2a, that's m1 plus m2 times a. So that's m1 plus m2 times a. And let's draw a little barrier here. Okay, that goes away. And so we get the acceleration, therefore. I'm going to factor the g. Get g out. And then here you have m1 sine theta 1 minus m2 sine theta 2 minus m2 sine theta 2. I need space times g. And then you divide by m1 plus m2. m1 plus m2. And so you get the acceleration. Let's say, hopefully we get a positive value. So m1 is 2000, theta 1 is 30, m2 is 1800, theta 2 is 20, and let's do that. And so we get, let's see what we get. 2000 times the sine of 30, that will be 1000, and then minus 1800 times the sine of 20. Okay, great. And then times 9.8. And then you have to divide by m1 plus m2. That is 2000 plus 1800, that's 3800 divided by 3800. And so the acceleration is 0.991. Meters per second squared. Okay. That's the acceleration. We're not done, actually. We're not done with this problem. They say, what is the speed downhill? So it started here and went all the way down. So here's downhill. So by the time it gets here, right? By the time it gets there, let me call this one here x initial equal to 0. And this is x final when it gets to here. How much is it? Well, if this is 200, what would this hypotenuse be? Well, this is 30 degrees. So something times the sine of 30 degrees to give me 400, to give me 200, it means x is 400, right? So this has to be 400 for this to be 200 and this to be 30 degrees. Because the sine is opposite over adjacent, opposite over hypotenuse to give me 0.5. Sine 30 is 0.5. So I have an acceleration from here to here. I don't have the time. I could figure the time, but we don't really want it. So I have v squared. I will use motion at constant accelerations to get v final squared minus v initial squared is equal to twice the acceleration times x final minus x initial. So v final squared minus v initial, it starts from rest, so that's 0. 0 squared is 0. And then 2 times the acceleration, that's 0.991. And then x final is 400. X initial is 0. And so you get v will equal to almost the square root of 800. Let's see. 0.991 times 2 times 400 to the power 1/2 to get the, so I get 28.2 approximately. I get 28.2 meters per second. So if the brakes fail, it would be 28.2 meters per second. And is that fast? I don't, well, yeah, that's kind of fast. Times 3.6. That'll be about 101 kilometers. That's almost 65 miles an hour over 1.6. Yeah, it's like 63 miles per hour. And so, yeah. So that is that. And let's go to the next problem. This problem took us a long time. All right, let's get to the next problem and then pause this video and then get to another video. So probably have 3 videos in total. So let me see here. So the 5 gram coin is placed on a turntable. So it's placed on a turntable, and the turntable starts to spin, and the coin has friction between itself and the table. The coefficient of static friction is 0.8, and the kinetic friction, if in case it starts to slide, it's 0.5. They say the turntable very slowly speeds up to 60 RPM, and then they say, does the coin slide off? So if it doesn't slide off, it means the static friction hasn't reached the maximum, because before you start spinning the turntable, the coin is just at rest, and the static friction is 0. As you spin it, so let me take a side view here of the coin. So this is the coin on top of the surface of the table. This is like here is the turntable. Turntable is like this, and it's spinning like that. So the coin comes and goes like that. So we have a side view of it. What are the forces on it? Well, there is mg. There is the normal force. And then what else? Well, why does it spin? Well, you need, there is a radial acceleration, so there has to be a radial force, and that radial force is due to, who is the culprit? Well, it's only friction. It's not tied by anything, so it would be the force of static friction. Okay. So in the y direction, we call it the z direction, and this is the radial direction. So in the net force in that z direction, up and down, is equal to 0, because there is no motion up and down. And so you get the normal force minus mg is equal to 0, and therefore the normal force will simply equal to mg. The force of static friction, remember, force of static friction takes values between 0 all the way to some maximum value, and that maximum value is μs times the normal force, and μs times the normal force, which is mg. Okay? Those are the values the force of static friction can take. If the force needed to go around the circle exceeds this value, then it will just slide off. It can't support you anymore. The force of static friction does not support you anymore. So how much force is needed? Well, I know that in the radial direction, let's draw it here, the net force in the radial direction is equal to the mass times the acceleration in the radial direction. The net force in the radial direction, there is only the force of static friction. The force of static friction, that's it. And that has to equal to the mass times the acceleration in the radial direction. So that's the mass. The acceleration in the radial direction is, if you remember, v squared divided by r. And so let's calculate the force of static friction and then see if it exceeds this value. If it exceeds it, then you will slide off. So to do this, first of all, we have the radius, and I have omega here. It's 60 RPM. So let me just clean some things up. So we got omega is 60 RPM. Remember, RPM means revolutions per minute. We need radians per second, so times 1 minute for every 60 seconds, and then times 2 pi radians for every 1 revolution. And so let's see what omega is. Let me get my calculator. Let's see what omega is. Oh, that's nice. 60 cancels 60, so it's just 2 pi. Awesome. So it's just 2 pi, 2 pi radians per second. Okay, nice. And 2 pi is about 6.28. So omega is approximately what? 2 times 3.14159. About 6.28. Yeah, approximately 6.28 radians per second. So what's the speed? Remember, v is omega times r. V is omega times r. And so we go here. So we get the force of static friction that you need to do this would be m. V is omega times r, and you have to square it. And then you divide by r. And so you get m omega squared. And then you have r squared on top, r on the bottom, that's just r. So let's see what we get. So the force of static friction needed is m. What's the mass? 5 grams. So that's 5 times 10 to the minus 3, because it's grams. Omega is 2 pi, so that's 6.28, and you have to square it. And then r, what is r? It's, I forget what the r was. 15 centimeters from the center, so r is 15 centimeters. So that's 0.15. So what do we get here? Let's square omega and multiply by 0.15, and then multiply by 5, and so I get 29.6 times 10 to the minus 3 newtons. That's the force of static friction needed. So let's calculate this maximum force of static friction here. So you get 0, the force of static friction, and let's see if what we get here. Mus is 0.8. The mass is 5 grams, so 5 times 10 to the minus 3 times 9.8. So I get 39.2 times 10 to the minus 3 newtons. So the force of static friction can supply you up to 39 times 10 to the minus 3. Here you have 29 times 10 to the minus 3. Sure, so it's within the range. So it didn't slide off. So the coin, does the coin slide off? Answer is no. The coin does not slide off yet. So it doesn't slide off. All right, so I will see you in the next video. We'll do maybe 2 more problems, and that's it. All right.